Welcome everybody! Today I'll be talking about our paper towards practical doubly efficient private information retrieval. I'm Simon Pohmann and this is joint work together with my supervisor, Rachel Player, with Hiroki Okada and with Weinert. Before we start talking about doubly efficient private information retrieval, maybe I'll give a short overview on standard information retrieval, private information retrieval. It's the whole idea is that we want to query a database obliviously. So imagine a scenario where you have a client and a server, and the server contains a database of n entries, x1 to x capital N, and the client has an index I and wants to retrieve the ith element from this database, namely xi. In a normal retrieval situation, the client would now just send I to the server and the server answers with xi. However, in the situation of private information retrieval, we want it to be private, and so the server should learn nothing about the index I, or basically about the index I. Server shouldn't learn which element was requested by the client. A naive solution would now be to have the server send the whole database to the client, but the problem of this is that the communication cost of this approach would be basically the whole database, so linear in capital N. And when we talk about peer, we are usually interested in protocols that have communication cost sublinear in capital N. And the most traditional area, direction in which we design schemes would be this row in this table here that I've called stateless, which is very old, contains both old and new schemes. Among the new schemes, these three here. And the basic idea is that we somehow scramble the index I, for example using homomorphic encryption, and thus achieve a communication cost only polylogarithmic in n, but at the cost of still a linear computation time. Now the point is that a linear computation time is undesirable for applications that have very large databases, but it's very hard to avoid. The reason being that in some sense the server has to touch every element in the database. Because if he didn't read the jth element upon answering a peer query, he would learn that the client couldn't have requested the jth element. This has been formalized also by a paper I didn't list here as an impossibility result. But of course we've been interested in circumventing that impossibility result, and the most successful avenue to do this is this third row here of so-called stateful peer schemes that has been pioneered by the CHK peer, for example. And their main idea is to introduce a client-dependent preprocessing phase in which a client and a server interact to produce hints that are then locally stored at the client. The hints are much smaller than the database itself, usually of size square root n, and using these hints the client can then perform peer queries much faster, in particular, for example, communication and computation cost square root n. I think the slide is even not perfectly accurate because some very modern schemes even change the communication complexity here to polylogarithmic, but the computational complexity remains O of square root of n. Now, it has already been left as an option in the previous impossibility results that a client-dependent preprocessing is not the only way to circumvent the linear bound on computational complexity, but a global preprocessing phase might already be enough. So a preprocessing phase that doesn't have to be executed for each client, but can be executed just once before any clients are even known. And if we use this and at the same time achieve communication and computation complexity, both polylogarithmic in n, then this is what we would call doubly efficient peer. For a long time, about 20 years, doubly efficient peer has been an open problem, and thus giving rise to the other two avenues of peer schemes. But last year, this paper by Linmo and Wicks was the first one to actually propose a construction that achieves doubly efficient peer under standard hardness assumptions. I encourage everyone to read the paper, it's really cool and won the best paper award at Stock. Yeah, anyway, their paper, while really impressive, only considers it from a theoretical perspective, only considers logarithmic running times. And so many people, among them us, have asked the question, can we do it in practice? Like, is doubly efficient peer also more efficient than other peers in practice, in practical applications, and not just asymptotically? And this is the main question that we want to answer in this work. Before we delve into details, let's go to a few preliminaries. I already mentioned homomorphic encryption, which is like a very important cryptographic primitive for the construction of peers. The basic idea of homomorphic encryption is that we have an encryption scheme that allows us to perform computations on the underlying data. So in addition to an encryption and a decryption algorithm, we also have an evaluation algorithm that takes a function in the ciphertext and produces a new ciphertext. And if we decrypt that ciphertext, the result should be the function applied to the original message. So basically, yeah, we have a message here, we encrypt it, we perform the evaluation algorithm, which basically means, or which you say, we evaluate the function f homomorphically on the ciphertext, and then we decrypt and we get f of m. Most schemes that implement homomorphic encryption use algebraic structure. That means that the function f is given as a sequence of additions and multiplications, i.e. as a polynomial. And then the evaluation algorithm proceeds by applying a homomorphic addition or homomorphic multiplication in ciphertexts. Also, all the schemes we currently know that achieve this are based on lattices, and as such they include a noise in ciphertext that increases during homomorphic operations. This means that if f has contains too many operations, like if f has if f takes lots of operations to compute, then this noise could overflow and destroy the message. While modern schemes, like most of them that I've listed here, BF3, GSW, or CGGI, they contain measures to decrease the noise, but these measures are very costly, so we don't want to use them in the context of peer. Instead, we just use only functions f that do not contain too many operations and so do not cause the noise to overflow. Okay, it should be quite clear that we can build a like naive peer scheme from homomorphic encryption, and it would work like this. The server starts by, in a pre-processing phase, taking the database and encoding the whole database in a polynomial. More concretely, we would compute the interpolation polynomial f such that f evaluated at the point I produces xi. And once this is done, the client can now perform a peer query. It takes the index I, encrypts it under the homomorphic encryption scheme, sends the encrypted index to the server, and the server then homomorphically applies the polynomial f, db. And the result is then an encryption of the entry of the database, xi. Sending that to the client and decrypting gives the result. This scheme has very low communication cost, because basically we just send the index I and the result xi plus the overhead cost by the HE scheme. However, the computational cost is very high since f is very large. F has in some sense to accommodate the whole database, to encode the whole database. And so, in fact, one can easily see that it takes linearly many operations, at least, to evaluate f. Nevertheless, this kind of like idea or concept is the idea that underlies most of the stateless peer schemes and also the paper of Lindmo and Wicks, but in each case with significant improvements. In the paper of Lindmo and Wicks, we even need very heavy machinery now, because this blueprint here looks quite like it fundamentally takes time linear in n. However, yeah, the really surprising part is that they found a way to compute this evaluation of the polynomial here in exponentially faster than previously thought possible. by using very cool machinery, as already said. And this machinery comes from an original paper by Kedlaya and Umams. In fact, they're not cryptographers, but they've developed it for asymptotically fast algorithms for polynomial factorization, I think. And their main result, the result used for doubly efficient P goes as follows. Assuming we have a ring and a polynomial over that ring, then we can compute a data structure that will later enable us to very efficiently evaluate f endpoints. And this data structure has size given by discrete expression, and also computing the data structure takes basically time linear in its size, so linear in this expression. Here the poly term is not too large. M and D will be very small, and also log R is already logarithmic in the ring size. The interesting part is the second part here, and we will come back to that soon. Yeah, and after we build this data structure, we can then evaluate f at a point in only that much time. And well, I won't go into the details or the balancing the parameters here, but as it turns out, if you choose D and M correctly, you can make this here really small, in particular polylogarithmic only in the database size. So unfortunately, I think proving this theorem or showing the exact constructions of the data structure and the evaluation algorithm is beyond the scope of even this extended talk. I encourage everyone to read the paper. The Lindmo and Wicks have reproven this theorem in their paper because it's just very fundamental and might be easier this way for an audience, and it's very nice to read and very fascinating. But it also involves a nice amount of math. Anyway, once we have this theorem, we are almost where we want to be and almost get doubly efficient P. However, there's still one more obstacle, and that is that this theorem only applies to evaluating polynomials. However, while our database lookup FDB is a polynomial, the homomorphic evaluation of FDB is in general not. Especially for modern FHE schemes, this is not the case. Nevertheless, it's required, and so for the whole idea to work, and so Lindmo and Wicks defined this notion of algebraic homomorphic encryption scheme, which simply said just means that in this case the evaluation of a polynomial is again given by a polynomial. Or more concretely, the evaluation algorithm of a polynomial at ciphertext is just the evaluation of the polynomial at the ciphertexts. This of course means that we can add and multiply ciphertext, so we basically, the ciphertext needs a ring structure, the ciphertext space. This notion is more natural than one might think at first, and in fact it's what the first FHE or HE schemes that were constructed had. So in particular, like the very old schemes from when it was invented by Gentry, like Gentry's original scheme, or in this case the B scheme by Brakaski, they all have this algebraic property. However, the newer schemes, they don't have it anymore because they went away from it to do more clever things during the evaluation algorithms that have very positive impact on error growth, noise growth, and runtime performance. Anyway, we can't use these new schemes because they're not algebraic, and so we and also Lindmo and Wicks use the B-style scheme in their construction. And this is now the property that evaluation of FDB at a ciphertext is a polynomial evaluation, and we can use this previous theorem here, polynomial evaluation data structure theorem, to speed it up and make it in logarithmic time using a pre-processed storage, using like a pre-processed data structure of the polynomial. Okay, well, this sounds really nice. Why don't we just implement it? I've been like presenting it nicely and talking about, can we make it run in practice? Well, why can't we? And basically the problem is the constants become huge. Here, to give you an impression of how large they become, I've made a small example. we assume the database size is about 1 million, so we have 1 million entries in our database size. In this case, the ciphertext space of the B-style homomorphic encryption scheme becomes this ring here. Yeah, remember it must be a ring because it's an algebraic homomorphic encryption scheme. Set modulo 2 to the 1000, and then we take a finite degree extension of this, so we join x and y and mod out x to the 65,536 plus 1 and y to the 81 minus 1. And yeah, as you can already see, this ring is huge. The logarithm of its size is 2 to the 32, which basically means that a single ciphertext needs about 4 gigabit, I guess, 500 megabytes, but almost a gigabyte for a single ciphertext, which is huge. We can then, a reasonable choice for the polynomial FDB seems to be to take a degree 80 and 5 variables. Of course, other trade-offs might be possible, but we can't choose degree and number of variables too small because the polynomial needs to be able to encode that many, 1 million entries. This seems like a reasonable choice, but of course there's a trade-off here. If we now take these two values and plug them into this formula here for the data structure size, and we just take this like main contributing factor of the data structure size and evaluate it, we find that the data structure needs to have about 2 to the 65 entries, and assuming that each entry is a byte, this is about 30,000 petabytes. So yeah, we already see it might be not very useful, not practical to implement it directly. The running time is also quite high, because yeah, estimating this is not quite as simple because in fact the way they stated this theorem here, it only contains this doesn't specify the exact polynomial dependency on dm and log r exactly. In our work, we very precisely estimated all these values, and we then came to the conclusion that to run the scheme for these example values, we'd have to do about 2 to the 47 entries from this storage, from this pre-computed data structure. And if we assume the whole data structure is stored in RAM, which might not be realistic for 30,000 petabyte, but okay, then we can estimate the time to perform that many requests, and it's about 1,500 hours. Which is, I think, a very good reason not to directly implement the scheme. Nevertheless, since the original scheme has only been designed to have good asymptotic properties, so maybe we can improve it and make it also work in practice. And this was the guiding question for our research. Can we somehow make this practical? Can we reduce these numbers to numbers that are sane, feasible, or even competitive with other schemes? And to approach this, we looked at the inner workings of the scheme and proposed some improvements. And I want to tell you a little bit about the main two improvements because I think they're quite nice. And the first is to use the structure of this ring R here in more detail. And basically this is a technique that is already known in the FHE community as double RNS representation, or as Fourier or CRT representation. The basic point is that if we take the polynomial data structure and the evaluation algorithm, then the first step of evaluating at a point is in this case to reduce the input element from this ring here into a scalar ring. And now this scalar ring must be extremely huge because it must accommodate every element of the original ring, plus also there's some overhead that is required to ensure that this transform is compatible with the polynomial evaluation. So yeah, we have an absolutely incredibly huge Q. That's much larger than the size of the ring R itself, and R is already large. And this allows us to put into a scalar ring and then use some more magic from that theorem that I won't go into the details. However, we show that we can completely avoid this step if we choose the parameters correctly. And in fact, for many FHE schemes, this choice of parameters already the default because it also allows improving performance in other settings. In particular, if we choose every prime factor of the ciphertext modulus q here to be congruent to 1 modulo 2n times d plus 1, then this whole ring here decomposes already into a direct product of finite fields, fp. Of course, we still have a large number of finite fields, say if n might be 65,000 and d might be like 80, and then q might have multiple prime factors, so we still get a large number of finite fields. But yeah, after all, we can't really decrease the size of the ring R, that's fixed. But we can eliminate this overhead here, caused by this transform. And if you apply it to the parameters I had on the previous slide, then it turns out that this improves the runtime by about a factor of 55 and the storage cost by about a factor of 3000. Okay, now let's go to our second main improvement. And to this, it deals with the choice of the polynomial FTB. In the paper by Linmo and Wicks, they choose FTB as an interpolation polynomial that has degree d in each of at most degree d in each of the variables xi. And if we fix the d, then it turns out that the number of monomials of the resulting polynomial is d plus 1 to m. And of course, since we can encode at most one database entry per monomial, we need d plus 1 to the m to be at least n. However, the cost of using all the machinery, of using the homomorphic encryption scheme and of using the preprocessing polynomial evaluation data structure depends not on the individual degree in each xi, but on the total degree. And in fact, the total degree of this choice of polynomial is suboptimal, because this polynomial has now total degree d times n. But the monomials belonging to this degree are very few. For example, the FTB has only one monomial of degree d times n, and that's the monomial where each xi has degree d. Nevertheless, we pay for this high degree, but we don't really make use of it. We just make use of it by one polynomial. So instead, we propose to choose a different FTB that is where the total degree is restricted, and this total degree we define the total degree of a monomial to be the sum of the degrees in each variable. And now, instead, if the total degree is at most d, then we find that the number of monomials of FTB is d plus m choose dm, and this must now be larger than n. And this is an improvement in basically the database size that we can work with of about d plus m choose m over d over m to the m. If we forget the 1 here and use capital D, the total degree is n times d. And using Stirling's approximation, we find that this is about e to the n. So we support a larger database at the same cost. And applying this to the previous techniques, we again additionally improve the runtime by a factor of 8 and the storage cost by a factor of 100. Okay, yeah, apart from that, we also have some minor optimizations, which I won't explain in this talk. I think there's not much to gain from them. And we can now return to the results of the project and to the question, is doubly-efficient peer practical? Some of you might already have done the computations in your head, like multiplied the improvement factors I've noticed here with the original cost, and you might already have guessed that the answer is, well, not yet. We still have quite high cost in both in terms of runtime and storage. Anyway, we demonstrate that dpeer is now at least implementable, which means, yeah, we have an implementation that can run this dpeer protocol for at least small values. And given that previously, the storage size was in the order of many petabytes, this is already a significant improvement. Yeah, and now I also don't want to hide from you the results of our implementation, even though they can't really be called practical, but still I think it's interesting to see how fast this scheme can operate in practice. We've run the example on a database we've run the scheme on an example database with 46,000 elements, which admittedly is quite small. The communication cost seems, well, high, but sane. The storage cost is in this order of magnitude, is 1 terabyte, which also seems reasonable. The main problem is the runtime, which is 30 minutes to answer a single peer query. And that's much higher than other current asymptotically suboptimal peer protocols achieve currently. However, I said the runtime to perform a single peer query, which is only half correct, because the way this B-style homomorphic encryption scheme works, it supports a single instruction multiple data parallelism. So in fact, instead of doing just one peer query, we can, at the same cost, perform a large number of peer queries by embedding them all in the same ciphertext. You know, the ciphertext is large. This is not just all of that is overhead, well, most of it is overhead, but also the plaintext space is quite large, and we can embed many peer indices, and we will retrieve xi for each of these indices at the cost of just performing a single query. So if we take this 30 minutes runtime for a single query and amortize it for each of these slots, then we will get 55 seconds, amortize milliseconds for each of these entries. And, well, in fact, this number is almost competitive, at least if you don't take too much care to use batched peer protocols to compare with. Yeah, we can then also use the data collected during smaller experiments to estimate and extrapolate it for larger examples. A standard example is the database size of 2 to the 24 and 2 to the 30. And in these cases, we have very large storage requirements of 800 terabytes, respectively 400 petabytes, which admittedly is already very high, maybe better than 30,000, but still it doesn't really seem very practical. And also the runtimes are like in the order of many hundreds of hours. Again, amortizing makes them look quite nice, even though 10 minutes is still high, but makes them look somewhat nice. But given that a scenario where we have to perform thousands of queries at once might not be realistic, and then even then latency might be an issue. Okay, so yeah, we don't claim it's practical, but we still think this is implementing this, showing that this can be implemented and run, at least for smaller parameters, is already quite a surprising result. And I think if you look at the literature, many authors of papers have in fact quite doubted that this is the case, that we can at least implement this scheme. Our implementation is written in Rust and publicly available. So if any one of you wants to join this line of research and try to make doubly efficient peer practically yourself, then you're very welcome to use our library. That's it. For any detailed questions and the inner workings of this polynomial evaluation data structure, I refer to either our paper or the paper by Linmo and Vix. And I thank you all for listening, and hopefully see you at Financial Crypto. Many thanks!